So I'm at a company called CoreOS. How many have heard of CoreOS? Fantastic, so I don't have to try to give you the sales brochure. I can kind of skip that part. And I'm this guy, I'm Kelsey Hightower on Twitter. I like to tweet now, so I just tell people to tweet me. And then that's the last slide we're gonna deal with, right? So it's gonna be ad hoc, because we're gonna be talking about stuff I should probably not be giving a presentation on, because it's just that new, right? It's like literally, they're still making commits of probably core features, so I can't be doing anything from tip right now. And we're gonna talk about a project called Kubernetes. But before we talk about Kubernetes, I gotta ask you guys a few questions to see where we're at as far as like our understanding of like infrastructure. How many like ops people here? All right, you guys are pseudo ops. Do you do backups? If you don't do backups, you're not ops. Yeah, you guys are not ops. How many people think their ops team likes them, their dev team?
Likes them?
Yeah. Do you know why your ops people don't like you?
You don't do backups.
That's one, right? The reason why ops people don't like developers is mainly because you treat them as, the best way I can think of it is like a try except block. So you write all this code and like these mock unit tests and they like, hey, pass. And then you just throw it in production and any exceptions, you hope they catch them, right? And you're just like, yeah, we got ops people, I'm going home. And we wake up and we be like, why are there so many errors in the logs? Like errors are bad, right? And you guys are like, well, just ignore those. So Nagios is going crazy. And I'm like,
they're good errors.
Yeah, like good errors. Those errors are okay, right?
Yes. And
And we have like other keys you can use, like info, I'll take warning, but just fix them. So your ops people don't like you because you do that to them. How many people here actually know how to deploy their code, like for real? All of it. The database included, the whole nine. I don't believe you. So one thing that's important is like the operating system, right? Like the OS. And this is kind of where things start clashing, is where you build maybe on your local machine. Like to me, I write a lot of Go code these days, so I'll dev on my OS 10 box and I'll make a binary or check it in CI and it builds a binary. And luckily I don't use a lot of C Go, so there's not a lot of library dependencies that we run into. But if you're writing like Node or Ruby, I've seen some really bad like miscommunication is what I'll call it. And in production, you do a deployment, and some people's deploy process is like npm install at runtime. And you don't know what you're going to get, right? It's really exciting if you're an ops person, because you're like, is it going to actually start up this time? And if it does, everyone kind of goes and cheers. This is why they're always stressed out. So one thing that CoreOS is trying to do is force a model where the contract gets a little bit more explicit, where, you know what, this container thing seems like it's going to work out well. It solves a lot of other reasons, not just a packaging format. Like today, I think we all use containers as a RPM replacement. And what I mean by that is, today, if you're using stuff like RPMs or devs, basically what you're doing is saying, my app depends on these other things on this local system, right? And then you hope that people only deploy one version of your app and everything will be true. The minute we try to put two of your apps on the system, it all goes out the window. Or someone says, you know what, I want to use Ruby 2.0 now for my project, then it gets a little bit weird. So now with containers, you really get to say everything you depend on in like a Docker file, if you guys are used to Docker, and you give me a container. I don't need to look at it. I just launch it. If it runs, we're in agreement. It starts up. If it doesn't work, give me another container, right? So then we get happier. So what CoreOS does is says, you know what, that's the only way to deploy. There's no package manager, there's no apt-get, there's none of that. You can't even write to the root file system. It's not available. So a lot of admins get mad at this because they want to put like their vimrc files or Emacs and like set up a home directory. It's like, that's not what we're doing. This is strictly for deploying application code. So we start with this operating system. And a lot of people like this idea of a read-only operating system, so we shrink things way down, right? So out of the box, CoreOS comes out and says, you know what? The only thing you really need is like the ability to launch a process and start computing, and you're done. And then what we do is say we scrap everything else, right? There's going to be no utilities. If you need a utility, you bring it in a container, and we'll talk about what that means. So we reduce the size. So now these things are easy to deploy, net boot, push around. And now we're starting to get into this world where we can do atomic updates. So this is a new concept. A lot of times you jump on production if you do updates. A lot of people just don't do updates, especially if you're in the cloud. You take the AMI Amazon gave you, and you're just like, that's good. until they delete my AMI, and then you get another one. But in reality, you should probably do updates. But most people are afraid of updates. Why? Because most of your code has too many dependencies on what people are updating. So when some guys like, dude, I just turn on automatic updates, and you get a new version of Ruby, and the world stops, right? And then your ops people find another reason to not like you. And what we do here is, since we have a hard split between containers, your apps, the things you bring in, and the actual OS, we can just update the OS all day long, right? So by default, CoreOS takes the model that Chrome does. Chrome doesn't ask permission to do the update. It may ask you permission to apply the update, but it doesn't ask permission really to do the update. So what CoreOS does by default, and you can turn it off. That's like one thing I had to stress. People get really nervous by saying, you're going to automatically keep me up to date and secure. This can't be. I need those heartbleed situations. I need those emergencies. So we're trying to remove those emergencies. So by default, what we do is, if any of you guys have ever dealt with like networking equipment, very common because that stuff just can't be going down and it needs a way to roll back. We do the same thing. We have two partitions. We have an A partition and a B partition. So you come up with the newest version of CoreOS, and over time, it will check in just like Chrome using the same protocol that Google introduced with Chrome, the Omaha protocol. So we say, hey, I'm running version foo. And it says, you know what, bar is available. And it says, you know what, I'll start downloading that to partition B. And when that's complete, either if you have it configured with the default settings, it'll go through and reboot itself. And in CoreOS, it's really designed for like cluster setups. So we also ship a distributed key value store backed by the RAF protocol. So if you're really deep into like this RAF and consensus algorithms, it's a way for us to say, look, we have at least a permanent data store that lives on every machine, and we're sure that everyone will get the same notification. So we can do things too, since it's distributed, we can do things like implement locking cluster-wide. So if you want to control your reboots, you don't want your whole cluster going down at the same time, right? Lights go off. You can actually say, you know, I want to do one at a time. And they will decide to reboot themselves by grabbing a lock on the global or the distributed store and reboot themselves one by one. If anything goes wrong, they can reboot back to the A partition. And you don't have to do anything with your apps because those live on another partition where you can do user level stuff. So once you like that model, and we force this whole container thing on you, how many of you guys have played with Docker at all? Are you guys using Docker in production? There's a reason why the hands don't stay high, and this is what we're gonna. This is the focus of the talk, because Docker is absolutely awesome. I think it's like a dream come true when you start talking about this contract between dev and ops. So instead of giving me package.json, just give me the whole thing, and I can guarantee you that thing will run. So we can use the same thing in Jenkins, same thing on your laptop. So when it really works on your laptop, there's a really good chance it will work in production. Today, that's not necessarily true. So we force these containers on you. And the nice thing about Docker is that it's really like a single host solution, right? You log onto a machine and you do Docker run and everything works well. Or you can step back and use the Docker API and give it the same type of commands. But that doesn't say anything about what the cluster should be doing. So basically what you're doing is you're pinning your applications one-to-one. And every admin in the world used to this, right? It's like, I got Puppet and I have a list of host names, right? And you name them after like Transformers. You run out of Transformers and you go to Power Rangers and My Little Ponies. Then no one knows what's going on anymore, right? But the host names look awesome. But then you run out of host names, right? And then you're like, dude, we got to rename all these things. And then you have a bunch of meetings, like what the naming convention should be. And then those go long. But this is all because we care about the host way too much. And the reason why we care about the host, devs, you got to help ops out. You got to write apps that don't assume the database is always up, right? Like I've seen where the database goes down, the apps like launches missiles. Like, dude, the database could go away. You can't start wars because the database has gone away. So to help that out, if you make your apps kind of be able to degrade gracefully, like the network went away, your apps should say, you know what, the network's down. I'll just write to the logs letting people know the network is away. Don't blow up and stop and shut yourself down. Don't do that unless you're Node. You have no choice. But I shouldn't talk about Node. But I have to balance it out with the Java stuff. So it works well on one box. But the thing is, you have all these containers. But the biggest problem, if you guys have ever played with Docker long enough, and you start launching them, you're like, where did the container go? Like, what port is it on, right? So you're doing all this stuff trying to keep track of the ports. So, but you're doing all that on one machine. Imagine on 1,000 machines. Someone's like, hey, where's that container? It's like, oh. And then bash, like for loops, looking for containers. Oh, it makes your laptop get warm. You don't want to go in that world. But the concept is still awesome. So now we have this better packaging format. Docker makes it really fast to deploy the thing that we want. So then we move into this world where we want to do this kind of cluster thing, right? And ideally, most people do have clusters. Right now, we just think of multiple machines behind a load balancer, and they're pretty stateless. So most people have already moved to this path of my application is stateless. You just send it traffic, it does something, and it connects to a database. This is why so many of you raise your hand about trying Docker, because you've already been doing this with VMs, right? It's just that the container format was so big, it came with too much weight. Now we've shrunken it down to containers. So what we're starting to see now, or what Google has seen a decade ago, is having a bunch of containers. And I think about containers as just regular processes. Some people like to think of them as virtual machines. And when you think about them as virtual machines, you start doing stuff like, oh, I have this container, let me put SSH in there. Let me put Nginx in there and Logstash. Like, see, you're going too far. It's just a process. So once you think about it as a process, then you start building your containers in a way that they're single purpose. But then you do want certain things to live together, right? So you may have, in some cases, a web front end that may want caching to be local to it, right? For speed purposes, right? You get to a certain scale, you're not going to use a single memcache instance. So you may want to keep that close. But Docker doesn't give you a way to really say much about that, right? You say, you know what? I got a bunch of containers. I'm going to go on this host and spin up all the things that it needs. And we'll see what Kubernetes does to solve that problem. But one nice thing we have is this distributed key value store. So every host will have this available on localhost. So this kind of gives you an easy way to configure all your machines. So if I know that everyone needs the database passwords, you have a couple of options today. You can actually rewrite your app to read from etcd and say, you know, I'm going to watch this key space. And I'm going to look for my app name / database password. And I'm just going to watch it. So etcd supports the semantic of like watch, where you just hit a key and you just stay there until you get an event. So that way in your apps, you can do like this dynamic config thing. So if I change the password in one place, every app that cares about that password will take action, right, and automatically reload themselves. So once we get into this world, a lot of people are actually doing this. Some people are using like Puppet or Ansible or various configuration management tools to do something similar, but we got to know about those host names. But what etcd is, we remove the need one more step about the host name, because it doesn't matter where they live. I only need to talk to etcd on one machine, and the value will show up on every other machine. So what does that look like really quick? So if I'm on machine A, so this is the master setup, and I have a 3-node cluster going here, I can do a command called etcd control and set foo to bar, right? And if I go to another machine in the cluster, I can do etcd control get foo, right? And then if he changes it, set foo to bar 2, right? And this guy should be able to get the value. And it's just real time, so you can count on this by default on every single node to have this like cluster state manager. So it really makes things easy to do configuration management real time, right? So now that we have this cluster set up, all the machines now have like a communication channel. It's not a replacement for RabbitMQ, but it's something where you can do configuration around. Then we have a bunch of tools that help us distribute things. And we have this concept of service discovery. But today, service discovery is kind of raw. You spin up a container, and one thing you can do is say, you know what, I'm a container, and I live on this box with this port with this IP. Very tedious. Your app will have to know way too much. So, but if your app did do something like that, we can have like load balancers watch this key space as things appear and go away. But you got to write custom tooling here. So what we want to do is solve this problem. So we're going to end up in this world where there's just containers running everywhere in the network, but we need to know where they are, and we want to access them, and we want them to be able to talk to each other. So what do? We use, not conft, but you can, we use Kubernetes. How many people have heard of Kubernetes? Guys are on Hacker News, like, you got to get some work done at some point. Like, oh, what's this Kubernetes thing? How many people know how Kubernetes actually works? So good, I've been spending a couple of weeks like, submitting test fixes and bug fixes, documenting, writing blog posts. And ever since this thing hit the ground, it's important to CoreOS because now that we're in this world where, some of the people we're working with, they want to run thousands of machines, doing deployments and not worry about host names. But there's a missing component. Docker is not enough. CoreOS and etcd aren't enough. You need a scheduler on top. And some of you may have worked in infrastructures that have scheduling. And with the scheduler, all you want to do is say, I have this unit of work, it could be a container, and I need 8 of these. And you let the scheduler go and figure out what machines are the best candidates to run that workload on. It'll pick the machines, it'll assign the ports, and it'll give you an interface to find them all very easily. But this is actually something really, really hard to do. So what Google has done for us is tucking a lot of what they've been doing in the past, and what they learned were like some of the pain points. And in this time, they didn't just write a white paper. They actually gave us a reference implementation we can actually use. So there's this project called Kubernetes. It sits on top of the operating system in Docker, and it wants to take over the responsibility of launching and managing the containers. So this is drastically different than SSH into a host and run Docker run. In this case, we're going to look at a container manifest. And basically, we're going to give a declaration for what a workload looks like. And there's a couple of concepts that we're going to introduce really quick from the Kubernetes standpoint. So Kubernetes has this idea of a pod. And the pod allows us to do that thing we talked about, right? There's this web API that needs that caching service next to it, needs to be local to it. So one easy thing that Kubernetes does, which is a big departure from the way Docker works. In Docker, when you spin up a container, it gives it its IP address and its port and does a dynamic mapping. Kubernetes is like, Docker, I don't need you to do that anymore. I'm going to spin up a network container that just does nothing but handle all of the networking. And what this means is that first container that comes up, he'll have the IP, and he can proxy all the port communications for that IP to the containers that care about it. So what this means is we can take a pod that can be composed of multiple containers. If you think about multiple containers, here's your web app. Here's the thing that may be collecting logs in a separate container. And here's the thing that does your caching in a separate container. But they get deployed as one single unit. So what Kubernetes does is give us the semantics to deploy or describe what that unit is. So if we look at Kubernetes, and we look at one of its examples. So we'll look at the API example. Actually, be easy to go over here. API is what we want. So this thing's changing. Everyone's still moving things around. So we'll look at one of these pods. Here's a pod. So I can give a pod an ID, right? I give it an ID, and I say, you know what? This is what the desired state is, not what host to run this container on, but this is what I desire. I desire that we're going to use, this is the endpoint API. I have this thing called PHP, right? And this PHP needs these containers. In this case, there's one container. It needs Nginx, right? This is the specific container that we need. And here's the name we want to give that. And then here's the port mappings that I want you to do. The container will be binding to port 80. But I want you to map everything to port 8080. And this host port is important because this sets us up for something called labels. And I don't think we have any, yeah, we do have a label here. So this service is made up of n number of containers, but we may say, you know what, this is our billing service. And our billing service will get traffic that comes in on port 8080. So this is our liveness probe. And anything that hits any of the servers inside of the cluster, any of them, even the one that's not running the container, has a proxy on it that say, hey, I don't have that container, but I know who does. Let me proxy that TCP connection for you, and I'll handle it. So now service discovery becomes trivial. You hit any node in the cluster, and you're routed to the right application. And the only thing you need to know is the service port. You don't need to know anything about the containers, their names, or what they're running, just the actual service. But remember, a service can be made of a collection of things. So you deploy them as a unit. So let's see what that looks like. So what happens is in Kubernetes, there's an API. So we saw that little graphic there, right? We do things through the front door. We can either hit the API directly, basic HTTP stuff, but there's a command line tool called kubeconfig. And kubeconfig will take in different commands, like creating a pod. We'll start with pod. And it will tell the API service, here's a manifest and state of the cluster for this one pod. Its job is to say, all right, I'll take that. But there's other people responsible for doing things. There's a proxy service. His job is to look for new services made of pods to show up. And he will set up the proxies on each box dynamically. And they all watch etcd for those keys. This is how it does it real time. So if you have 1,000 nodes, all 1,000 nodes get this notification that they should be proxying for port 8080 right now. And then we get a replication controller. We're not going to talk about that yet. But you may say that, you know what, I need 3 copies of this pod running somewhere in my cluster. And its job is to find homes for all of those pods. Here's etcd in the middle, so distributed service. And then you have the kubelet. Kubelet is responsible for doing what you've been doing, logging into a machine and running Docker run. But the kubelet does a little bit more. It also makes sure that it's always running. If it died for some reason, it will bring it back. If a machine disappeared completely, the API service will move that work to someone else automatically. So if you just drop a machine, it will update the key space and say, you know what? That kubelet that was doing this is no longer there. I'm going to take the work out of his namespace, so if he comes back alive, he doesn't start running it. We'll move him into a new namespace for one of the other minions. And these guys over here say, oh, you got work for me to do. You told me that I'm responsible for making this container run. I'll do that. So let's see what that looks like. I'm going to jump on the command line. And I have my 3-node cluster running in VMware right now. So it's a 3-node cluster. And I'm on my Mac running the commands with the kube command. And so what I can do, if this works, I'll be so proud of myself. Because this is definitely risky. I'm usually prepared, but it's like, nah, this is too much of a moving project. But we'll see. So what we can do is look for that example. And before we run this, I want to make sure that there's nothing actually running, no pods up and running. So we can use our key space here. We can list pods. We have none, right? Nothing scheduled to be running anywhere. But we can add one. So we give it a config. And then we say, I want to create this manifest, but it's going to be a pod. So we're going to create it to the pod's namespace. So what happens is a bunch of operations go. API service says, all right, I got it. Now it's time to start processing that manifest file. And now it's going to start giving people tasks. So the first thing that happens is it's like, all right, I'm going to find a guy worthy of running this job. Either he has the best CPU. So the scheduling is pretty simple right now. It's more like a random who can do this work that's not already running the same pod. I can. You win the lottery, you get the work. So when we do list pods, that guy, number 10, won the lottery. So he has the work on him, right? And he's running the container. Now, if I ever wanted to know where this was, like if I wanted to bring in a load balancer, I can just use this label query to say, show me all the things in the foo service. And it will return a list of IPs and ports that I should hit if I want to get there. So now that we have this thing running, we have this thing called PHP running on that host. I actually don't really care too much about that host. I can just pick an IP inside the infrastructure and hit it. So let's look at that pod again. We said we were on 8080. Yeah, from here we said we're on 8080. So let's see, and let's see if this still works. So 192.192.68. 10, let's see. So we said it was on 10, right? Let's see if a proxy actually works. So the proxy worked. So a box that doesn't have the container on it doesn't know anything about the workload at all. Separation of concerns. But he knows someone in the cluster has the workload. And Kubernetes behind the scenes says, you know what? If anyone comes to you looking for this service, send it over here. And you don't have to update anything. So if you do new deployments and you bring things up and down, it automatically updates this real time, nonstop. This is different than like a Puppet run, right? Where a Puppet run, you would say, all right, we're going to do this Puppet run, and we're going to iterate through the host. And then you got to make sure you got them all. In Kubernetes world, is they don't stop polling. Does there work for me? Is there work for me? So if it misses the first loop, it's back again. And we can see this actually in the logs. So if we go, CoreOS uses systemd, by the way, so that means a lot of things are different than what you're used to. So there is no log files per se. Everything's a big binary rotating log file that are written like a JSON type format. So we have to use a tool called journal control. And journal control, I can either watch for all the logs, or I can be very specific and say, you know what, I only care about this guy. In this case, we care about the proxy. What was the proxy doing? So what the proxy is doing is there's some debugging stuff, and he's looking for keys of work to do. He can't find some of those keys. And some of these errors are just debugging because Kubernetes is like a really early project, and we're trying to find a lot of bugs in it. But it's watching etcd looking for things that it should be doing and responsible of. But if we look at the logs for the actual guy that got the work, this guy. So the master server is also running a kubelet, so he can actually schedule work himself. The proxy, he's already done. Let's go to a pass. Let's look at the kubelet. So he doesn't stop watching the namespace. He just keeps looking for work to do. And when he finds it, I think some of our work has flown off the screen. There we go. So we're at the top of the log. So I'm doing F so I can tell it. So it found some containers and some ports. And it's like, oh, I have a container that I'm responsible for. Until that key disappears, it's going to always make sure that it's running on its system no matter what, nonstop. I'm going to try the one that's multi-nodes where we're having multiple Redis slaves. And what should happen here is in this new pod manifest, we'll go to, here we go. There's a controller. So in the controller set, we'll say we want 2 of these pods. And let's see if we get better luck here. So this is the controller example. And what we're going to do is fire this into the cluster. It's going to do the same thing, but says I need 2 copies of this Nginx thing. And we're going to use the same proxy port. So let's see if we actually get our stuff scheduled this time. So it looks like we got failure for some reason. And I could debug it, but I don't want to sit here that long. So what normally happens is, so I actually know why this is broken. This guy has a port conflict. The Kubernetes service runs on port 8080. So right now, the guy that won the lottery is unable to schedule the work, right? He has a port conflict with the API service. And if I remove it, I'm going to edit this pod.json. Actually had a pull request like, why are the examples with conflict? So what's supposed to happen is it should never go to that host because it's not eligible, all right? And this may be just some bookkeeping that we need to do in the code base, but it should have never happened in the first place. All right, so yeah, Vim is like the cure-all. So let's put this guy on a different port really quick and see if we get better luck. And we did delete, so we're going to create it again. And now we should have a different port. And this port should have no conflicts. I'm not even sure why it worked the first time. Because you saw it work. Well, the proxy should, no matter what host you hit, it should just work. So let's see if this actually does the right thing. If it lies to us again, then the demo gods have. Oh, so this guy wins. You guys are clapping. So I've actually been hacking on Kubernetes a lot, and I just knew that bug because I ran into it a few times. I started like really having second thoughts about my career choice, like maybe I should do something else. But then I realized it's a bug. It's not my fault. And so, okay, now it's working. And so this is the network container we talked about. You can't control this container. It grabs the IP, it grabs the port, and it almost renders Docker useless for telling you things about the port. You can no longer talk to Docker. You have to get things from Kubernetes at this point. It's now the boss, right? And now when we go to our machine, we won't get lies. I bet I had like success cache the last time from something that was working. And I don't think I have the proxy server set up here because we didn't set up a service. And that's by design, because a service is a different object. So we did the single node pod thing. So what we're going to do now is a more advanced example that also brings in a service. All right, so we'll go back to our examples. So this has no service endpoint. The pod we just did is say, you know what, just spin up this container, don't give a service for it or a proxy for it. Now what we're going to do is introduce one that does. So there is a multi-tier application that they have in the project, and we'll use that. And there's like this guestbook application. It basically has a Redis master, 2 Redis slaves, and 3 nodes effectively handle web requests. So it should exercise every member of the cluster. So we go over here to examples, it's guestbook, and basically we get all these steps that we really have to do right now. So what I'm going to do is basically copy and paste these things on my machine. So the first thing we want to do here is spin up the Redis master. And this is just one node or one Redis box coming from Dockerfile, blah, 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 running on that port. And we're going to give it a label so that when we give it a label, when other machines that need to connect to this master, it can use environment variables because environment variables are seeded into every container launched by Kubernetes. So you can get to the other services that you need to talk to. And we'll see what that environment variable looks like in a second. So actually, I can just run this. So this is the guestbook example, and this is the Redis master. So we jump back on the command line really quick. And then we do kube cfg. And then we'll do examples, guestbook, Redis master. Right? We need to create it, and it's on pods. So we'll create the Redis master. So what this should do, if this container is not on your server, Docker will do the normal thing, go to the index, pull down Redis. I preceded all my machines earlier with all of the containers that would be part of the demo, so things will go much faster than in real life. Or we'd be sitting here waiting for Docker to do its initial pulls.
Is pods significant? Could it just as well be bar?
I think the concept of pods is like peas in a pod. So like you talking about this namespace? Yeah, it's significant. If you don't use pods, that means nothing because no one cares about that namespace.
Okay. I thought it was dolphins. Oh, I guess that makes sense.
Dolphins, pods?
Yeah, 'cause they have pods.
Not related.
Oh.
It can be, but not today. So really quickly, this guy found a guy to run our Redis server. So now we have Redis up and running on node 1, right? So node 1 won the election. And we get here, and then we do our list again. And now we see we have two things, right? Just dynamically found something. But we don't have a service label yet. So we can't necessarily use the proxy thing. So the next thing we want to do is bring up that actual service. So this is what a service configuration thing looks like. This is important that they're decoupled. So you can do like rolling deployments. You may want to change things around. They shouldn't be coupled. A lot of times when people have written their tools, they just decouple. They couple everything into one big JSON blob. If you want to do things independently, it just doesn't work. So Google has really brought their experience to the table with this by saying, nah, trust us. You're going to want to do some of these actions independently of each other. So here we're going to create the actual service proxy. And basically, we're going to just take this example from the guestbook. I don't trust the documentation because sometimes they're out of sync because things are moving pretty fast. And so now we're going to basically use the services namespace. And we're going to get a new service that pops up. And that's just telling all the proxy servers that their job is to set up a proxy for what we care about. So if we do journal control -u proxy and we tell it, they should find some work to do here. So this error we got, you can actually give work through a text file. So you can drop a file in place and it says, oh, there's a new file, you want me to do something different. You can either talk to it through etcd like we're doing here. So here it says, oh, someone just gave me some work. There's a new service that popped online. And here's for this Redis master. And it's going to proxy for it, right? Automatically, we didn't tell it to do much. So now that we have those bits up, and this guy should be done. All right, and so we have a service, and that service label is how you find all the nodes in the pod if they're spread across multiple machines. So now we're going to proxy port 10,000. We'll always come back to that Redis master that we have. It's decoupled. So that's the proxy port. And if you look on all our machines, you will just see automatically that we have 10,000 binded on the machine. So any one of these you hit, you're going to get redirected. All right, so the next thing, and we have a couple more steps and then we'll be pretty much done, is we're going to set up a Redis slave controller. So the concept of the controller is to say, you know what, I want more than one, right? And now I'm going to say, you know, I want 2 replicas of the following pod. And we call it a pod template just because it's going to get reused. And we also give it a label so we can actually find all the Redis slaves in the cluster by doing one label query. So we'll just run this again. So now we're going to create a replication controller. And the replication control is a little bit smarter. If anything goes away, like too many things come up or too few, it brings things back in alignment by keeping state across all the machines. All right, so we'll spin this up really quick. And don't think it's this fast always. Like if you have none of these containers on your machine, at least the base image, you will wait a long time for that first Docker pull. So it's really, you got to be really careful about how you do that. Where are we at? Wow, is that like a bug in the actual Redis code or the actual JSON? All right, who can spot it?
Go on, name slave without comment.
Where?
Name slave, there's no comment at the end.
You should hurry up and do like a pull request.
Dollar sign.
Dollars. Capital A, comma.
You ever see Vim users try to like teach new people Vim? Like, what are you doing? Oh my God, is that the mouse? Put it down. It's like, dude, I'm scared. It's like, just chill out, we're gonna be okay. All right, so that's a bug. All right, so now we have this controller is gonna get set up. And its job is to find a place for these two things to run. And let's see who wins the lottery here. So we found one host already. So this guy happens to be running 3 things. That's pretty quick. And then this other guy, no Redis slave there. Oh, and then we found another one. So we're done, right? So we have that part set up. So now we have the master and the slaves are connecting to the master. And you'll see how they're connecting to the master. So when they get deployed, inside of the container, that's the command that's being run. This guy comes up and says, I'm using the service host, which is the IP of my host that I was deployed on, and I just want the Redis master service port, 10,000. I don't care where it is. You just figure it out for me. So things can just launch and be portable across the cluster. This decouples the whole, oh, what machine is it on? That's out. You can just deploy things like this. So with these environment variables, if your applications you build support environment variables, then you can have this decoupling even from the infrastructure itself. So if you get out of the config file mode, because it's hard for me to write a config file dynamically all the time, this is much easier for me to deal with. If you do this pattern, then I can schedule you anywhere in the cluster. So now we'll just look at the pods that we have. And then we're going to get to the finale where we see if this actually all works. So there's our services. And here's our pods. All right, so we have our slaves. And there's 2 slaves running. They happen to be on different hosts. And you see their labels, so we can do label queries about them. And then the last thing we need to do is, we'll have 2 more things. We're going to set up some label queries for the Redis slaves themselves. So some of our nodes will actually read from the slaves and write to the master. And this one is on okay, the slave JSON. All right, so now we're going to create a service to proxy to all of those Redis slaves, because we don't want to ever configure our apps to know where those containers are, because they might move. All right, money that this works the first time. Whoo, success. I'm so surprised it even got this far. Like, I was so prepared to do like another talk halfway. It's like, you know what? We're not going to talk about Kubernetes anymore. We're going to talk about something else. And we didn't have to do that. So now we're going to do, we have our service in place. We're going to validate that the service actually works. And once the service is up, we'll be able to deploy. And this, I don't know why they chose a PHP application. Did they write PHP at Google? Hope not. Okay. That would be bad. Ah, so they wanted to make it believable. Okay. Yeah, you know, PHP needs some love. You got some love. So now the last thing we're going to do is set up our 3 instances of our web application, right? So you can imagine the ops guys taking care of the Redis setup and all that stuff is there for you. And you, the developer, would say, you know what? This is the spec that I'm going to give the cluster in production. You push this in. So you built the container with your app, more PHP. So you have the container, and you know what you need. So inside that container, you know how to look for Redis and those things. And you just give it the state. And you don't really care about which 3 nodes. You just know it needs to be 3 nodes. Now, the scheduler is pretty simple now. It's like randomly you win. But you can also do things, and it's actually on the top of the tree, there's CAdvisor support built in. So CAdvisor does more metadata gathering about how much CPU is actually used on a box. You can also do things like with some of the scheduling and launching of C groups is limit how much memory and CPU each container can have. So if you're crazy like Google and you want to pack the last CPU of every box, you could if you implemented all of those things to do the accounting. So you can say, you know what, none of my servers can never be more than 50% full. That way, if I get one of these ad hoc jobs, I can say there will always be bandwidth for those ad hoc jobs. And soon Kubernetes will be smart enough to locate a machine that has enough compute for your job. So if there's 3 that are better than the other 7 out of a 10-node cluster, pick these 3 because they have more CPU. Today, that's not the case. You'll see like uneven traffic going to host. There's not much you can do about it. But in the Kubernetes model is when 3 of these hosts get overloaded, then it doesn't meet the requirements for one of your services. Let's move it to another member of the cluster. That's a very powerful concept because now you don't need someone watching graphs. Like how many people just like got the graphite up on the TV? And it's like, oh, graphite, and then you run back and you try to do something. And the funny thing is ops people just laugh. And so that goes away now. So now it's like paying attention to those things. And what I think will happen in the future is there'll be other things that we can collect and do that ourselves, like to add custom things. So it's kind of like what you get from Amazon if you ever use like their CloudWatch stuff and auto scaling. But now we don't have to tear down whole machines, we just move workloads around. Don't do this with your Postgres database. Like, if you do, let me know so I can laugh, but don't do that because it's going to be really funny when people can't get their data. I don't think it's really good for that workload yet. So what we're going to do now is launch the 3-tier application. Now what you can't see is my other hand and my fingers across that this actually works. And what should happen here is we should have a bunch of containers, and now it's really a PHP app, I can't believe it. We'll be running on all 3 nodes, and we'll have this little guest book, right? Someone wrote some PHP because here's the source code. Like, what made someone feel the need to write PHP? We're going to put a pull request to make this go. Like, we have to change this. So let's look at it. Let's see if we're done yet. And what we should see here now is everyone has the PHP app. So we have all our network containers. You notice that the thing you normally see from Docker, this is not your pods in the container, right? This is the actual network container, and they all share IP space. That means if you have multiple containers in one pod, they need to have different IP addresses, or they will clash by design. One thing, too, that you may not notice, which is different from Docker, all of the containers here can talk to each other, right? Container foo can talk to container B. And the way this works is we use a different bridge. There we go. So I set up this other bridge, and what we do here is we give it an IP in the 10 dot space, and we basically give each host its own subnet, 254 usable IPs, well, 53 because you can't use this one. And what happens is the way Docker works, Docker looks at your bridge and says, oh, you're dot 1, so the container gets dot 2, up until a point where we run out of space. So like I think it doesn't hit 254. So if this was dot 10, it'll start at dot 11 for the next one. So this is what Docker does out of the box. It doesn't use DHCP. Kubernetes would prefer to be the one that manages the IPs, but Docker does that for now. But you can imagine a world where even Docker will lose that responsibility. It doesn't really need to be doing that, but we just use it because that's just the way Docker works. But that also makes it easy to build systems like this because you don't have to handle it. Docker does so much for us on a single host. So now we're up and running. Let's list the pods one more time. And ideally, everything should be running, right? So we see the 3 PHP Redis applications, don't we? We do. So ideally, we should be able to hit that on our services port. Well, not services port. We can actually hit the actual IP in the manifest. We don't necessarily need a service for that. So that's 8,000, all right? So any of the hosts, it should work. So if I go here on 8,000, we got failure. Don't fail on me now. We're like almost finished. Let's see what we're listening on here. Yeah, 8,000 across the board. Who knows what's wrong? Oh, I saw that coming, man. Oh, there's one of them. He's happy. Let's see if another guy is happy. He's happy too. You can't expect PHP to be too reliable. Yeah, so we'll ignore this guy for now. We'll figure out what's his problem. So we should be able to write something here like PHP is better than Go. Stop hating. All right, so we do that. And ideally, if we go to this other guy, and if the Redis master and slave is working, he should see that message already. It works, right? So our whole backend works except for the other guy, all right? And so we go back and forth, and our actual app works, minus the other host, but pretend you didn't see that, right? Who knows what's wrong with that guy? He's just not happy, right? So we don't know what's wrong with that guy, but overall, it's working. But what's happening now, though, in Kubernetes, and I don't have the tip of the branch, is there will be a health check on that port. The liveliness will fail, and it will be restarted or moved to another host until it works. So right now, the liveliness check isn't there yet. I actually have only a stable version that's actually working. And commits are flying in all the time. But I think in about a month or so, when this thing really hardens and we get the health checking, the C advisor support, we'll be really close to having this thing that gives you that cloud-like functionality anywhere. So you can actually run Kubernetes and GCE. It'll work on like a VMware setup, your local machine, bare metal. And then you can have this common API. So instead of using like an Amazon control panel in one setup and then like Vagrant in another, now you can just have like these pod manifests. And you give it to GCE. You can give it to your local API running on your local machine. And this concept is also nice too because like for integration testing, you can just generate a nice manifest of all the services required and push them out. Run your integration test and then just delete that replication controller, right? So now you have an easy way of specifying this stuff. So this is the idea of Kubernetes. This is the problem it's trying to solve. Forget about the host names. Try to have a self-healing cluster. And you need all these components to do it. And like I said, this stuff is really, really early. No one claims that this particular component is production ready. But the nice thing is they've opened it up really early for people to start understanding the concept and ideas. And it's in a form that you can actually start playing with it and see if the semantics make sense. And if the semantics make sense, then we'll have a tool we can use. If they don't make sense, speak up. These guys are really responsive with communication, and they're always listening to what we want to do. So to me, this is the future of infrastructure. This is probably what we will all be doing eventually, because no one wants to log into machines and run a bunch of command lines, right? You might have people keep the conveyor belt running, but there should be multiple people that can push work into the cluster. We're kind of doing this already, but it's really ad hoc and a bunch of scripts and tools that don't really work well together. Now we're starting to formalize all those practices into new tooling. So that's the end of the presentation. That's Kubernetes. Thank you.